Hello everyone, welcome to our today's presentation. The title of the presentation is An Intelligent Approach for Power Quality Events Detection and Classification. As can be seen, most of the participating authors are from the King Fahd University of Petroleum and Minerals at Dhahran, Saudi Arabia. We have two authors from Australia, one is Mr. Joel Rana and other one is Dr. Asif Islam. Myself, M. Shafiullah. Currently, I am working in the Center of Research Excellence in Renewable Energy at King Fahd University of Petroleum and Minerals. All of the authors of this article can be reached through the provided email addresses. Now let us start the presentation. At the beginning, we need to know what are the power quality events. What do we mean by the power quality events? These are the most frequently used buzzwords in the field of electrical engineering. You can find the definitions of power quality events in IEEE standards, IEC standards, different electrical engineering textbooks, and so on. As you can see, this is pure sinusoidal signal as required for all electrical AC appliances. However, their magnitude can be little bit lower for a specific period of time or for a few cycles than the expected values. Or the magnitude of the signal could be little bit higher than the expected. Or the magnitude of the signal could be close to zero for a few cycles. Or there will be some harmonic components in the signal. Also, there could be spikes or notches in the signals as well. All of the mentioned events can be classified as the power quality disturbances or power quality events. The second question is, what are the reasons for power quality disturbances? In answer, we can say massive deployment of nonlinear loads, solid-state devices, power electronic converters, higher penetration of renewable energy resources and distributed generators are the main reason for power quality disturbances. Power system disturbances can also occur due to power system faults, lightning strikes, energization of transformers and large capacitors, switching on and off of large electrical loads. Third question is, what are the consequences of power quality disturbances? The power quality disturbances may lead towards failure or malfunctioning of electrical protective devices. They can damage the sensitive loads or they can damage the relay protection system. Overall, the PQ events can lead towards economic losses by damaging the equipment or reducing the production pace in the industries. In grid level, the PQ events can cause a wide range of problems including power system instability. Considering the gravity of the topic and the recent addition of power quality event producers like the renewable energy resources, the management of power quality events has become very crucial to the power system operators. Before 1990s, the power quality events were monitored and managed manually. However, the technological evolution, including advanced metering infrastructure, smart signal processing, data mining, and artificial intelligence techniques, along with high computing devices, paved the way for better management and monitoring of power quality events in recent years. Thus, power system researchers reported different schemes for power quality events detection and classification, combining advanced signal processing and machine learning tools. However, the reported articles rarely employed the meta-heuristic algorithms for performance improvement of the PQ events detection and classification schemes. In this article, we have mathematically modeled 8 different PQ events, including the pure signal. Then we have employed an advanced signal processing technique, namely the Stockwell transform, to extract the useful features from the modeled events. Then we have systematically selected artificial neural network models for power quality disturbances detection and classification. The weights and biases of the selected ANN models were optimized employing a meta-heuristic optimization algorithm, namely the Gray-Wolf optimizer. Then we have compared the performance of the optimized ANN models with the non-optimized ANN models for both detection and classification problems. Finally, we have investigated the robustness of the developed schemes under noisy measurement conditions. Now let us have a quick look on different signal processing techniques. For example, the Fourier transform. It is one of the greatest tools used in engineering applications. However, it cannot deal with non-stationary signals like power system signals as it loses temporal information. In response, to deal with the non-stationary signals, the short-time Fourier transform was introduced. However, it faces resolution issues as it uses a fixed sampling window of regular interval. To resolve the resolution issues, the wavelet transform was introduced. However, the wavelet transform does not contain the phase information and sometimes it is sensitive to measurement noises. In response, the Stockwell transformation was developed. It combines the advantages of short-time Fourier transform and wavelet transform. It contains the phase information as well as it is less sensitive to measurement noises. These equations represent mathematical modeling of different signal processing techniques. Now let us have a quick look on machine learning tools. The machine learning approaches develop the models that are trained and tested using the known information or data, where both inputs and outputs are known. Then the developed models are employed to provide decision on similar events, where the inputs are known but the output are not. The artificial neural networks are the widely employed machine learning approaches to solve real-life problems. Because they are capable of parallel computation, also they are adaptive to external disturbances. Other machine learning approaches include the decision trees, support vector machines, and extreme learning machines. To tune the parameters of the selected neural networks, we have employed a recently developed meta-heuristic optimization algorithm, and the name of the algorithm is Gray-Wolf Optimizer. The algorithm consists of several steps, such as initialization of the Gray-Wolf positions, fitness evaluation, leader selection, checking the termination criteria, updating the Gray-Wolf positions, checking the boundary conditions, and so on. The algorithm starts with initialization of the Gray-Wolf positions randomly. However, at the end of the algorithm, it provides a near optimal position as the best solution. The optimal position is basically the position of the leader of the wolf pack, which is also known as alpha wolf. This table shows the mathematical models of different PQ events, including the sag, swell, interruption, fluctuation, notch, spike, and harmonics. As can be seen, there are different parameters in the third column of the table. By changing the values of the parameters, we can generate different number of samples for each PQ event. Now let us have a look on the modeled PQ event. We have the pure signal, we have sag event, swell event, interruption event. We also have the fluctuation event, the notch event, the spike or transient event, and finally we have the harmonic event. As stated earlier, this equation represents the Stockwell transformation of a signal x of t. After the transformation, we get a matrix S, and the elements of the matrix are complex by nature. The columns of the S matrix pertain to the time and the rows pertain to the frequency. By taking the square of this matrix, we can get the energy matrix of the signal x of t. Now from the S and E matrices, we can evaluate four vectors. One is SC max, which is maximum absolute values of the columns of the S matrix. The second one is SR max, which is the maximum absolute values of the rows of the S matrix. The third one is SC phase max, which is phase angles associated with the elements of SC max. The fourth one is the EC max, which is the maximum absolute values of the columns of the E matrix. Then we can evaluate the standard deviation, maximum value, minimum value, mean value, entropy, skewness, and kurtosis of each vector. Eventually, we will have a total of 28 features from the signal x of t. To select the better configurations of the detection and classification neural networks, we have tested them with different number of hidden layer neurons, different types of squashing functions, and different types of training algorithms. Through the systematic trial and error approach, we have selected the number of hidden layer neurons, squashing function, training algorithm as given in this table for the detection and classification neural networks. It is worth mentioning that we have used 70% of the available data for training and rest of them for testing of the neural networks. This table shows the MSE values of the PQ event detection and classification neural networks with different number of hidden layer neurons, where the 10 sigmoid was the squashing function and Lebenberg-Marquardt was the training algorithm. This table shows the PQ event detection and classification results under noisy and noise-free measurements with the non-optimized neural networks. These are the MSC convergence curves while optimizing the weights and biases of the neural networks employing the Gray-Wolf optimizer. After optimization of the weights and biases of the neural network, the detection accuracies have been improved. For example, under noise-free measurement, the detection accuracy has been improved from 98.98% to 99.54%. Similarly, the optimized classification neural network outperformed the non-optimized classification neural network in terms of overall accuracies under both noisy and noise-free measurements. Now we are at the final part of this presentation. In this article, we have developed the PQ events detection and classification schemes combining the advanced signal processing and machine learning tools. We have modeled the PQ events mathematically and employed the Stockwell transform to extract the features from the PQ events. Before selection of the better models, we have tested the classification and detection neural networks with various configurations. Then we have tuned the weights and biases of the detection and classification neural networks employing Gray-Wolf optimizer. Presented results confirmed that the optimized neural networks outperformed the non-optimized neural networks in terms of detection and classification accuracies. Finally, we have investigated the effectiveness of the developed PQ events detection and classification schemes in the presence of measurement noises. That's all from our side. Thank you for listening.